All right, I'm using headphones so you can't hear the dogs barking. So we missed out on Rescorla or on Kamin, so I'm going to do a little bit talking about Kamin, and then I'm going to talk about this week's Rescorla's control groups, and I think that'll catch us up to speed for some important discussions. So what we're going to do is share my screen here, and we're going to share here, and we are going to go to our slideshow, I hope, and talk about some theories of classical conditioning, which is where we're leading. Now, I told you before I lost power last week about the equipotentiality principle. Now, remember, it's wrong. But basically, the 1940s, early 50s behaviorists believed that the choice of any conditioned stimulus, unconditioned stimulus, response, reinforcer, or punisher is completely arbitrary. That we choose it and set up the contingencies or the contiguities, and therefore the animals respond to it, or even us humans respond to that in that case. And that's how it is. So they claim that any CS can be paired with any US. Any response can be governed by any reinforcer or punisher. Once an item, and they always believed that reinforcers and punishers were things, not activities, not events, but they were things you could hold in your hand, so to speak, that once a reinforcer or punisher existed, always and for everyone in the organism's class, it was the reinforcer or punisher. So if you like Barney stickers in the second grade, you should still like Barney stickers today. They believed that biology was irrelevant to the learning situation for classical and operant conditioning, and that anything can be learned. I don't know if you got the idea that they were wrong. Right? No, we know that the choice of responses and contingencies are not necessarily arbitrary. Some are better than others. That not any CS can be paired with any US. Not any response can be governed by any reinforcer or punisher. Certainly, we change what we like as reinforcers and punishers over time. And what I like is not necessarily what some other 60-year-old likes. And that biology is extremely relevant to what we do. So let's move forward from there. So when we're talking about classical conditioning, we have to agree that there is a critical CS-US relationship. The important or critical things to note about classical conditioning is that the CS must predict or precede the US. It must come before. The CS must predict the US. So even though it comes before, it's not necessarily prediction. Prediction is going to be the more important part. And if the CS does not predict the US, no conditioning occurs. And the CR, the conditioned response, does not have to be identical to the unconditioned response. And again, even Pavlov noticed these differences, and the conditioned response can even be opposite to the unconditioned response, which we'll talk about in a couple of weeks. So any response is classically conditioned if it occurs to a CS, after the CS has been paired with the US, but it does not occur randomly to or does not occur to a randomly presented CS-US pairing. And we're going to demonstrate this as we go. But first, let's talk a little bit about Kamin. So there are a variety of theories prior to Kamin and then post-Kamin about why classical conditioning works. Pavlov tried the stimulus substitution theory and the perceptual gating theory. So he believed that this CR was simply a substitute for the UR because the CS was a substitute for the US. But we know that that's not always true because the CR can be opposite, or we know even in saliva is physiologically different. The perceptual gating theory, which Kamin actually talks about in his paper, suggests that animals that don't respond to a particular CS didn't perceptually gate it. They didn't allow that stimulus into the brain, and therefore the animal never even saw the stimulus and therefore couldn't learn it. Kamin comes along with the surprise theory, the idea that an animal must be surprised to learn. Rescorla and Wagner are going to come along with their computational model that can actually explain mathematically why surprise theory is correct. And then we've gone into current, more attentional models where the focus really is on how does the animal attend to and process various stimuli in comparison to other stimuli and events. So what's the Pavlov's stimulus substitution theory? Basic premise of SST says that the CS substitutes for the US. With repeated pairings between the CS and the US, the CS becomes a substitute for the US, and thus the response initially elicited by only by the US is now elicited by the CS, which sounds pretty good, except we have a lot of data that shows that that's not quite true. Right? This theory was doing well until they discovered compensatory conditioned stimuli and to conditioned responses, and now we actually know about the saliva differences. Some of the criticisms and flaws is that the CR is almost never an exact replica of the UR. An eye blink to the UR of a pear puff is a large and rapid closure, where the eye blink to the CS of a tone is a smaller and more gradual closure. Again, it can be smaller and more gradual because it has time, where the puff of air is right there. In defense of the theory, Hilgard in 1936 tried to explain why there were differences in the CR and the UR. He said the intensity and stimulus modality of the CS and US are different. Thus, we have to expect differences in response magnitude and timing because of the differences in CS and US intensity. The CR should be less intense than the UR. Might explain the saliva differences, but it still doesn't explain the compensatory responses. And so the stimulus substitution theory kind of has gone away, shall we say. A bigger problem is where many USs elicit several different responses. As a general rule, not all of these responses are later elicited by the CS. The conditioned stimulus seems to select for certain responses. So again, we go back to 1937, and Zener did a study with dogs. We presented the dog with food as a US. So food elicited a number of UR responses to food: salivation, chewing, swallowing, etc. When he began to classically condition the dog, so he used, I think it was a light, to predict the presentation of the hot dog, he found that they didn't get chewing or swallowing, just the salivation. Okay. On the other hand, Zener found that the conditioned response may contain responses that are not part of the unconditioned response. Zener found that the dogs turned their head to the bell, but they didn't turn heads to the presentation of the food. So the responses are not identical and may contain behaviors not in the class of the original unconditioned stimulus pairing. So the CR may be physiologically different and add more behaviors, and at the same time, it doesn't do all the behaviors you do to the unconditioned stimulus. So again, we have some significant differences between the CR and the UR, suggesting that they're not really just substituting for one another. So they modified this SST theory. And Hilgard said, only some components of the unconditioned response are transferred to the conditioned response, because a CS, such as a bell, often elicits unconditioned responses of its own, and these become part of the CR. And this was kind of what was the sign tracking study we talked about, where the dogs follow the hot dog. They emphasized this in the change of the form of the CR versus the UR. And Jenkins, Barrera, Ireland, and Woodside, 1976, did something similar. So in sign tracking, animals tend to orient themselves towards the CS, not the US. They approach the CS, and they explore any stimuli that are good predictors of important events, such as the delivery of food. So yes, only some components of the UR are transferred to the CR, and the CR may begin to elicit behaviors that you only do to the CS, but this still is not a substitution. It seems as if the animals are following predictors or attending to predictors of the unconditioned stimulus, not just substituting one for the other. Again, we've talked about Hurst and Jenkins, and then Jenkins, Barrera, Ireland, and Woodside did another study with the training, and they did the initial training, followed the light, and the dog tracks the sign. But the strongest data against the SST theory are the paradoxical conditioning, or the compensatory response. Black in 1965, so we're left the 30s, we're up to 1965, found that the heart rate decreases to the CS paired with shock. Well, when you get shocked, your heart rate increases, but when they see the light, the heart rate actually decreases briefly. So the US of the shock elicits a UR of a heart rate increase, but the CS, or light of tone, elicits a CR of a heart rate decrease. And again, that was one of the first demonstrations of a compensatory response. And Siegel in 1979, and we'll read some of his work, in his morphine studies, found evidence of actual cell downregulation in addiction. It's a cellular process in which the cells actually prepare for the upcoming drug. And this suggests, again, that it's not a substitution, it's a preparation for and attending to important stimuli that predict the upcoming US. Perceptual gating theory is the idea that only if the CS is biologically relevant will it get processed. Okay, that's a better idea than the SST theory. So it's saying, okay, only if it's biologically important does it get processed. So if a CS doesn't get processed by the brain, it doesn't get into the brain, into the cortical areas, it can be predictive, right? And we know that animals attend to biologically relevant stimuli. The problem is the data show that under certain circumstances, a stimulus is attended to or processed, but the animal still doesn't respond to it. So again, the perceptual gating theory is suggesting it never even gets into the cortex, that the brain simply doesn't accept the stimulus. It's irrelevant. It never even processes it perceptually. The data suggests, oh yeah, the animal saw it or heard it or felt it or whatever, but didn't use it as a predictor of the upcoming US. And so the perceptual gating theory doesn't seem to have a lot of data. Now, how do we know this? We have to look at Kamin's work from 1967 to 1974, where he began to work with blocking and overshadowing. We talked last week about overshadowing is when you use one weak and one strong CS. So we have a really bright light with a soft tone, or the opposite, a big noise with a small light. And we're going to train the two CSs together. Okay, what's called compound conditioning. So both the tone and the light occur to the US, but the reaction to the weaker stimulus is blotted out by the reaction to the stronger CS. And indeed, this was demonstrated by Pavlov, and he called this overshadowing. It's the idea that the stronger stimulus that uses a CS blocks out the weaker CSQ. So again, we have CS strong plus CS weak predicts shock, which is causing avoidance. The CR is strongest to the strong CS. Again, it's strong if we test the CS alone. If we use the weaker conditioned stimulus, we get a weak CR. Not surprising, but they still can't explain it. We'll get there, don't worry. So that's overshadowing. Big things overshadow little things. Blocking is a little bit different, and this is what we read last week with Kamin. You train one CS, and then you add a second CS to it. So you train light equals shock, avoidance. Good, we get avoidance. Then you go light plus tone is shock, and you get avoidance. And you get avoidance to this compound. But if you test each individually, only the first one learned, so the original learning, in this case the CS to the light, do you get avoidance? To the second one, so the second half of this, the tone, you do not get any conditioning. You get little or no avoidance. So you find that only one CS supports the CR. One stimulus blocks learning to the second CS. And this was, again, demonstrated by Kamin in a variety of studies where he demonstrated that this was a relatively robust phenomenon, as was overshadowing. And he used, over 1,200 rats to demonstrate this, that indeed the animal did process it, because if I just taught shock, at least we got a weak reaction, so that suggested the animal was at least hearing the tone in this case, or seeing the light in other cases. So it wasn't the perceptual gating, it wasn't the stimulus substitution, but something else was going on here. So again, his original blocking experiment, he has 4 groups of rats. The blocking group receives a series of light trials, and then a series of light tone trials. So group 1 didn't get the first test, just got tone. Second group got light only, and they tested tone. Well, if you only got the light and you'd never heard the tone, you wouldn't show any response to it, and they didn't. He tested tone only, tested tone. By George, they were pretty good. Light tone only, test tone. Yep, they didn't get it. Couldn't figure out that compound after teaching light alone. So again, here we have it mapped out here. Here's a control. I teach light. I test tone, nothing. I teach tone, got a reaction. Teach light tone, test tone. Yeah, the tone was good enough. I got something. I train light first. I train light tone, no CR. Right? The tone can't be processed. And again, we can equate the number of trials here. So we can have 24 trials here, 24 trials here, 24 trials here, 12 and 12. Interestingly, we can go 12 and 24 and it doesn't change the outcome. The things we know about blocking. The animal does detect the blocked stimulus. So this can't be perceptual gating. We get extinction of the CR with either tone alone or with light tone. But extinction occurs faster with the compound light tone. Okay? So when we do extinction, it occurs. It occurs faster using the compound light tone, which suggests that the animal did indeed detect it. It is independent of the length of presentations of the CS and the number of trials of conditioning to the compound CS. However, you must keep the US, the unconditioned stimulus, constant from phase 1 to phase 2, or you don't get blocking. Blocking is influenced by the type of condition response measure used. The CR it's fairly stable. It's better than some others. The nature of the conditioned stimulus may be important. You have to use a good modality for the animal. Tones are not going to work with a deaf dog. The intensity of the CS or US stimuli are important because if they're very large, it's harder to get blocking if they're very small. But what blocking depends on is the amount of conditioning to the blocking stimulus which has already occurred. It depends on, let's go back here, to how many trials I give here. If I learn this to asymptote, I can train this till the animal is nearly dead, and I'll never get a reaction to the tone. If this is learned to asymptote, which usually occurs under 10 trials, then the animal is not going to learn this and never respond here. Why? Yeah, he's used up all his learning to hear. He's not surprised by the addition of the tone. But how can we make him surprised? Well, we can change the intensity of the US from the two phases. So we can go from a 1 milliamp shock during the light to light tone predicts a 4 milliamp shock. Is this surprising to the animal? Well, I know I'd be surprised if I got 4 times the intensity of shock than when I was originally learning. Is the animal surprised? In this condition, yes. And in fact, we can also reduce this to half. So we can have a 1 milliamp shock to the light, and then a light tone predict a 0.5 milliamp shock, and the animal will again be surprised. So I quickly condition to the compound stimulus if it predicts something different than the original conditioning. I change the intensity of the CS. So I have a bright light to shock, and then I have a dim light with the tone. Well, this is now different. It's a different learning situation, and I won't get blocking. All I'll get is some generalization here. Oh, both bright lights and dim lights predict shock and tones. So again, what's happening? What's happening is the animal has to be surprised. Yeah? So perceptual gating is not true. SST is not true. Yeah, they hear the tone. The good explanation is Kamin's surprise theory. To learn requires some mental work, or to be conditioned requires some mental work on part of the animal. The animal only does mental work when he's surprised. And what's the biological genetic advantage of this? It prevents having to carry around excess mental baggage. I only learn when there's something different. There's no reason to learn anything more when it's always the same. Well, no. Let's learn when the change occurs, because change gives me a new context and a new situation. So the situation must be different from the original learning for the animal to attend to it. The better explanation is going to be the Rescorla-Wagner model. that the particular US only supports a certain amount of conditioning. And if one conditioned stimulus hogs all that conditioning, takes all that conditioning up, none is left over for another CS to be added. And the question is, how do we demonstrate this? Yeah, we will, don't worry. But first we have to do a couple things. We have to do a brief aside. And so this is where we get into this week's readings. And excuse Perkins. We must determine how a CS-US relationship works. Rescorla in 1966 spent a lot of time on control groups because it turns out that control groups in classical conditioning can make or break your experiment. So what exactly is a control group in classical conditioning? Why is this important? And is contiguity or predictability a bigger issue here? And I think you can guess which it's going to be. So Rescorla asked the question, which is more important, the CS-US correlation or the contiguity? And what is contiguity? Well, contiguity is close together in time or space. So you can have two objects sitting next to each other on the counter, and we can say that those are contiguous. But things can also be contiguous in time in that one occurs and then the other occurs, or they both occur in the same time. So there's some relationship between them in time. In the CS-US correlation, a CS is followed by a US in a predictive correlation. If there's a perfect correlation between the CS and the US, we can say that the correlation is perfect. The probability of the US given a CS is 1. And the probability of a US given no CS is 0, right? So think back to the shock. If there's a light, there's a 100% chance I'm going to shock. If there's no light, I know I'm not going to get shocked. But we know that life is not always a perfect correlation, and certainly most predictive stimuli in our world do not come at a 1.0 probability. So the question is, how is the CS-US correlation more critical? So Rescorla showed how two probabilities interact to determine the size of the CS response. So he used a CS of a 2-minute tone. So the tone's going to play for 2 minutes before the shock. And it's going to be presented at random intervals with a mean interval of 8 minutes. And group 1 had the probability of shock given this tone playing at 0.4. So there's a correlation of 0.4 between the CS occurring and the US of shock coming during that 2-minute presentation. Group 2 got the probability of shock given no CS as 0.2 between the CS and the US during that 2-minute presentation. Now again, we know that 1.0 definitely gets conditioning. But back in 1966, 67, 68, when he was doing these studies, they thought that it had to be in space and time. So because the shock always came during the light, they could say, oh, it's always contiguous. Yeah, but it wasn't always predictable or correlational. So which group, the 0.4 or the 0.2, should show more conditioning to the CS? Right, 0.4. It's more predictive of the CS. 0.2 is actually more predictive of the US occurring in the absence of the CS, right? Yeah. So based on that, he decided to look at how do we run a control group? If both of those were predictable, what's going on here? So he has a bunch of control groups he used, actually 6 types. He had a CS alone. The control group only gets the tone. So the CS is presented alone with nothing happening after it. Now, one of the problems with this control group is that you don't have the same number of US trials as the experimental animals do, and this actually affects extinction. Okay? Because what you've actually done in this situation with only presenting the light is you've made the light or the tone irrelevant and the animal stops attending to it. You can have a novel CS group as a control group. You present a novel conditioned stimulus to the control group, and you can look at whether the stimulus is truly neutral. But again, the animal doesn't respond to it because it just says, well, that was weird. You threw something in there and didn't mean anything. So again, the novel CS is not predictive. You can give the US alone, so I can just shock the animal without any CS. Well, this is kind of the same problem as the CS alone, I get lots of shock, but I don't get any predictive pairings. And so I'm not learning anything. Well, actually, I may be learning something about what's predictive, things that were irrelevant, or so the experimenter thought, that the rat picks up on is predicting the shock. Now, this is the one that people get hung up on. If I have a 50 or a 0.5, random 0.5 control group, that's the only true explicitly unpaired control. Because at 50-50, the CS never really predicts the US, but the absence of the CS also never predicts the US. So the presence of the CS is just as predictive as the presence of no US, right? To think of it, the light is just as predictive as no light. It's 50-50. So the animal learns a rule if it's 50-50. But if it's explicitly unpaired, if the light turns on, I'm not going to get shocked. What does the animal learn? And the animal learns, if the light turns on, then I'm never going to get shocked. So the light actually begins predicting the presence of no shock. So the explicitly unpaired group, as opposed to that 50-50, doesn't work. Backward conditioning, I shock them and then I turn on the light. Well, what happens is the shock predicts the light, not the other way. And we can have discrimination conditioning, a CS plus and a CS minus. One CS predicts yes, one CS predicts a minus. And this is the same problem as the explicitly unpaired and the backward. It works at teaching a discrimination, but it's not actually a control group. See why? The light means yes, the tone means no. But that's not a control group. What we have to do is do an actual 50-50. We don't want to use this explicitly uncompared. We want to use a 50-50. So whenever the probability of the US given the CS is greater than the probability of the US given no CS. Does this make sense? The light is more predictive than no light. Then we say that the CS is excitatory, and the CS now predicts the US. And the amount of learning is dependent on the size difference between the probability of the US given the CS and the probability of the US given no CS. Does that make sense? If it's very predictive, the light is very predictive, I learn faster than if it's just minimally predictive. Whenever the probability of the US given the CS is less than the probability of the US given no CS, the CS is inhibitory. The CS predicts the absence of the US. And again, the amount of learning depends on how predictive the CS is of the absence. So if it's 1.0, the light never predicts the shock, then the animal learns quickly. If it's 0.6, so 60% of the time, if the light turns on, there's no shock. It's not as predictive. Whenever the probability of the US given the CS is equal to the probability of the US given no CS, the CS becomes neutral because it doesn't predict and it doesn't not predict the CS. And that is at 50-50, and no learning will occur because there is no predictability. And this, folks, is our control group. We have to be really careful that we include a true control group, because people will try and use an absence of that the light turns on, it never predicts shock. Or they'll use, that's the explicitly unpaired, they'll use a CS alone or a novel CS. And these are useful, but they're not the true control group of a 50-50 relationship. Why is that important? Because this excitatory versus inhibitory is going to be very important for Briscoe and Wagner. It's going to tell us that we can expect learning to occur if the CS is either excitatory or inhibitory. If it is neutral, the animal doesn't learn. And we'll be able to demonstrate this using a mathematical model. So, is it important that the CS is correlational? Or is it that it's important that it's contiguous? It appears to be the correlation between the CS and the US, not the contiguity or the closeness in time, that is more important. And we can write this more succinctly, I guess. Correlation carries more information than contiguity. If a response is excitatory, okay, if it's plus, then it's excitatory. If a response is less probable, then it's inhibitory. And if the response is 0, then it's a neutral CS. Does that make sense? If I don't respond to the CS, it's neutral. If I respond less when the CS occurs, it's inhibitory. If I respond more when the CS occurs, it's excitatory. And we're going to use these words excitatory, inhibitory, and neutral as we move into the Rescorla-Wagner model. So classical conditioning, in a sense, is cognitive. Predictability is critical. And yes, oh, the horror, I'm in pain on this as a behaviorist. But I'm a modern behaviorist. I don't mind a little cognition there. And we are going to go into Rescorla next week. We're going to learn that learning occurs slowly, trial by trial. And each time the CS occurs and it predicts the US, the strength of that correlation is increased. So the trial 1, the light turns on and then the shock. Well, that's the first time this ever happened. So yeah, it's 1.0, but it's only happened once in that animal's life. It happens again and again and again. We're building strength of that correlation. So if we have an N of 100 times that the light predicted the shock, that's a lot better than an N of 1. So the animal is going to learn. But the learning curve is going to be monotonically increasing. It's initially a steep curve, and then it levels off as it reaches asymptote. We'll talk about this when we talk about Rescorla-Wagner. And we're also going to say there is an asymptote to conditioning to the CS. There's only so much you can learn about the predictability. And after that, it stops adding any more information, and so your curve levels off. And you'll continue to learn. But if you think about it, if I'm at 0.7 of my learning, and I'm going to 1.0, I only have 30 left, 0.3 left to learn, and that's going to occur more slowly than that first 0.7. And we can explain this using Rescorla-Wagner. But we're going to stop there, okay? Because I'm not going to give Rescorla-Wagner away yet. I'm not. And we'll see what happens here. Yes, we will. Oh, I lost my Zoom. All right. So, maybe not. I thought I was going to come back, but I don't seem to be coming back. There I am. Okay, we're back. I have electricity again. Hopefully this recording worked. Not as long, but we got cut back up on Kamin, and we'll talk about why this Rescorla-Wagner control models are so important. And they actually are when you get into applied situations, and it can help us understand phobias. It'll help us understand why dogs are reactive and all sorts of different things. But we're going to save that until Thursday. And I will see you then.